welcome to Conversations from the World of Allergy, a podcast produced by the American Academy of Allergy, Asthma, and Immunology. I am your new host, Rebecca Saff. I am a board-certified allergist and immunologist and a fellowship director who always enjoys learning more about the fantastic field of allergy and immunology. I'm excited to take on this new role as host of the Academy podcast. Our podcast series will use different formats to interview thought leaders from the world of allergy and immunology. This podcast is not intended to provide any individual medical advice to our listeners. We do hope that our conversations provide evidence-based information. Any questions pertaining to one's own health should always be discussed with their personal physician. The Find an Allergist search engine on the Academy website is a useful tool to locate a listing of board-certified allergists in your area. Finally, use of this audio program is subject to the American Academy of Allergy, Asthma, and Immunology Terms of Use Agreement, which you can find on their website. Today's edition of the Conversations from the World of Allergy podcast series will focus on the fascinating world of neuroimmunology. We are pleased to welcome Dr. Carrie Sokol as our guest for today's episode. Dr. Sokol received her MD PhD from Yale University, where she studied how the immune system recognized and responded to allergens under the mentorship of Dr. Ruslan Medzlitov. She completed her internal medicine residency and allergy immunology fellowship at Massachusetts General Hospital in Boston, Massachusetts. Her lab studies how allergic responses are initiated, particularly how neurons play a key role in this pathway. Dr. Sokol, thank you so much for taking the time to join us today.
Thank you so much for having me. I'm excited.
I'd like to start just by getting to know you a little better. Can you give us a one-liner about yourself and include something that you like to do outside of medicine?
Oh, goodness. I am your stereotypical, I guess, physician scientist that likes to geek out on the bench probably about 90% of my time and then see patients about 10% of the time. I get all of my best questions from my patients. So I love to learn from them and to then take those questions and kind of figure out the mechanisms or try to figure out the mechanisms in the lab. But kind of what keeps me running and what keeps me inspired on the day-to-day basis is actually all the music I listen to while I'm writing grants and thinking about science. So that is my thing. I love to discover new music and go to all these silly indie rock shows, which I'm happy to say there are plenty in the Boston area.
Is indie rock your genre?
Oh my gosh, it totally is. It has been since I've been 20 years old, and I'll never grow up. So there we go.
That is awesome. Do your kids like it as well?
They tolerate it. But luckily I have some nieces in the area that will go to concerts with me. So I'm not there by myself. So
Perfect. So what made you choose allergy immunology as a field?
oh my goodness. I feel like I went through every other field before I found allergy immunology. You know, what's interesting is that, as you mentioned, my PhD was actually in allergy. Like it was looking at the mechanisms that initiated allergic responses. So it would make sense to everybody else around me that I would become an allergist. But for me, it really wasn't something that was so obvious, probably because we don't get much exposure to it when we're in our training. So I went through the standards for MD PhDs, which were dermatology. I really liked dermatology, and I'm still really interested in immune responses in the skin, but I didn't feel drawn to the surgical side of it. I was really interested in really the fundamental, science within hematology and oncology, but it really didn't have that allergy focus that I was looking for. And ultimately, I found my way back to allergy after, a mentor, when I came to residency, said, you know what, you really, before you sign up for these other things, you should really check out allergy. And I tell people that it was just this happy accident of really just being surrounded by people that were thinking the same questions, that were wondering about the same things, that were the same type of crazy as I was. So that's how I kind of found it.
No, definitely. Once people are exposed, they learn how fantastic the field is.
You fall in love with it. And I tell people it's like one of those fields that's so amazing because you don't necessarily have to learn by flowchart. You don't have to learn by kind of protocolized medicine. You actually still get to think about fundamental physiology and fundamental immunology and how that affects people. So that's what I find so intellectually engaging and fun at the same time.
Perfect. So I want to talk about this fun field of allergy immunology. I wanted to start with kind of most people are taught that allergic responses are really evolutionarily designed to fight worms and parasites. That's why we have an allergic response. But it turns out that, of course, that theory is unlikely to be the whole story. And instead, there's this theory of toxins really being part of why the allergic side of the immune system develops. So tell us about the toxin theory, how we respond to toxins, and why you think this might be leading us to have an allergic response.
Yeah, so it's interesting because it all kind of comes back to how we discovered allergies in the first place. Okay. We discovered the allergic immune response, or at least anaphylaxis, which is, not a normal side of the immune response, but a true bona fide allergic reaction. We discovered that actually through investigations with the immune response to toxins. So, how did that happen? So I love to tell the story because it was at the dawn of vaccinology, kind of in like the late 1800s, early 1900s, when the Prince of Monaco was actually really interested in whether or not we could develop a vaccine against the Portuguese man o' war, which, as we know, is this related to jellyfish, kind of like a jellyfish, let's just call it, that had really severe toxin that would lead to lethal envenomations of sailors back then and actually still today. And the Prince of Monaco, he was so interested in this and thought, gosh, if we can make a vaccine against, cowpox, smallpox, different things, why can't we make a vaccine against this toxin and therefore protect sailors if they were ever to fall into the ocean and become entangled? And so he got his, buddies, Paul Portier and Charles Richet, to start studying this. And what was so interesting is that, they did what every good scientist would do. They start out with an experiment to find out what the lethal dose of this toxin was. And they went to repeat that experiment and to reuse animals, dogs in this case, that they had used in the first experiment. And what they found was really shocking because dogs that had gotten just a tiny dose on re-exposure of that toxin suddenly were dropping dead. They were having what looked like asthma attacks. They were having swelling of the skin, things that we would see now as hives. They were throwing up. They were having diarrhea, clear over the top anaphylaxis, which was so fundamentally different from what the toxin was causing on its own. And that was actually the discovery of anaphylaxis. And so if we look back into history, what we find, even as early, the Nobel Prize in 1913 in medicine, which was awarded for anaphylaxis, what we see is that original discovery was really made by looking at the immune response to toxins. Okay. The problem is that we kind of forgot all about that. Okay. And we left that to the side. The scientists went in different directions. They studied different things. And the whole field just kind of dropped it. And it really wasn't until around 1990 that this woman, Margie Prophet, very interesting person, developed single-handedly what she called the toxin hypothesis of allergy. And what was really cool about Margie Prophet is that she saw that the type 2 immune response, or the allergic immune response, would be perfect against toxins, okay? So she reasoned, okay, that the reason why our type 2 immune response was so immediate, why it just dumped out proteases and all these other kinds of enzymes to degrade things in the environment, was because that way we could actually get rid of toxins before they can do any damage to our body. So you need that immediacy because toxins aren't going to, wait days to replicate in your body like a virus or like even some bacteria. They're going to be immediately active. So she knew and could see that the type 2 immune response and its immediacy would really be helpful against toxins. And she also proposed that, gosh, one thing that a lot of allergens, maybe not all, but increasingly as we learn more about them, a lot more, that a lot of allergens had toxic activity all on their own. Okay, so we're talking about the proteases that we see in pollens. We're talking about the membrane toxins that we see in venoms. Okay, I mean, even we're talking about the haptens, things like penicillin and a lot of the drugs and contact allergens that we see, that all of these could change our host proteins, and by changing them, exert toxic activity. And so she really proposed two fundamental things in this toxin hypothesis. The first is that our body would detect the functional activity of allergens, and that's how things would get started up. And second, that the type 2 immune response would actually be protective against those toxins. And the crazy part is that, in the 20 years or so after she developed this hypothesis, we've been seeing again and again that this actually seems to hold true for the allergic immune response. If we look at these protease allergens that chew up things in the environment, well, if we kill that protease activity, we don't have an immune response against them. So it's that toxic activity, that functional activity, that's what we're recognizing. And also, it's really clear through work by Stephen Galley and Ruslan Medsatov that the type 2 immune response, and even IgE, is actually protective against lethal envenomation from snakes, from Gila monsters, from Hymenoptera, okay? And so all of this is starting to come together as a fundamentally different reason for an immune response, and one that is against toxins.
No, I'm glad that we don't have to deal with snakes on our way to work, but certainly I think that, that we see it in the venom. Certainly the toxin is initiating this immune response.
For sure.
And one of the things you've always been interested in is kind of how these type 2 responses, these allergic responses start. And that kind of got you into this path of neuroimmunology. Tell us kind of how nerves play into this.
Yeah, so I think the question of who was doing the sensing of this toxic activity was always something that was driving me, and always an interest for me. And the reality is that it was a long time coming, okay? And it was a long journey, because what we saw was that the immune cells themselves, all these important immune cells that usually get things started, actually didn't seem to be directly detecting that functional activity. And so, we kept on looking for what that sensor could be. And, a really funny thing happened actually to my 3-year-old at the time, which kind of changed our thought process on this. My 3-year-old got his first bee sting. And, it happens. But as an allergist, I knew that there's no better allergen really than bee stings, than bee venoms. And when he got his first bee sting and instantly started feeling pain and itch at the site, it was all of a sudden kind of this eureka moment for me that, you know what, his body is immediately seeing this, but it's not his immune system necessarily. It's his sensory nerves, okay? It's his sensory nerves that are allowing him to feel pain and itch. And so that led me in the lab, and this was right as we were starting the lab, to ask, okay, well, are sensory nerves first actually detecting other kinds of allergens? Is this just something specific to venoms? Or is this something that's shared between all types of allergens? And is that sensory neuron detection really that first step? Is it required for all the downstream activation? And so those were the questions that we kind of started the lab with, really unexpectedly, and really serendipitously, based on poor Will's sting. But then when we looked at that, we were able to see that, yeah, actually, if we looked at it specifically in mice, if we just exposed mice to, a papaya allergen that we knew that they were never exposed to before, okay, that they instantly were developing this itch response that lasted for about 20 minutes. So it was really transient, but it was there. And if we blocked that itch response, either by using kind of lidocaine drugs that would numb up the nerves, or by actually taking the nerves out of the situation completely using transgenic or knockout mice, okay, we were actually able to show that the nerve activation was necessary to start all the downstream steps of the immune response to this allergen. So then it really got exciting thinking about how this pathway, not only what all the different steps of it were, but really how this pathway could actually be regulated and regulate all the different types of the immune response and the allergic response.
So sometimes it's our patients that give us these great ideas in science, and sometimes it's our kids going to the park.
I tell everybody, about being a parent has actually made me a better scientist.
So we get these activation of these nerves in the skin, and then what happens next? So these nerves get activated by the toxin or by a protease, and then
Yeah.
what are they talking to?
So exactly. They need to talk to somebody. And really the first step in the immune response is really dendritic cell activation. Okay. And this is, of course, first step in the immune response to in an otherwise naive individual. So somebody who's never seen that allergen before. So how do they talk to the dendritic cell? And what we found was that when you talk to a dendritic cell, that dendritic cell gets activated. So it upregulates activation markers and it crawls into the draining lymph node where it can start up an immune response. So how is it instructing the dendritic cell to do that? Because we saw that if we take away the nerve, we lose all that dendritic cell activation, we lose that crawling, we lose that downstream immune response. So what we actually found was that there are neuropeptides that are released by sensory nerves in the skin, and they can get released just after activation, local activation, okay? So it can happen right there in the skin. And what we found is that specifically this one neuropeptide called substance P really seemed to be released, in high amounts after allergen exposure. And that we could show that in vitro with just nerves in a dish. We could show that in vivo in the skin, okay? And it's this substance P that acts on those dendritic cells to promote their crawling into the draining lymph node. And that was an essential step for all of the downstream immune response. But I would be lying if I said that that was the only thing that substance P was doing. Substance P was also shown by Nico Gaudenzio's group to activate mast cells that are hanging out in the skin right at the same place. And that mast cell activation from substance P leads to local inflammation and a lot of that local swelling that we really think of when we think of kind of immediate allergen exposure.
So that's on initial. So these are mast cells are being activated just by the nerve being activated
just by the nerve. Yeah. So you don't even need antigen for that, okay? Or antigen specific IgE for that. This is just a direct activation. And it really kind of gives us that neurogenic activation that sometimes we see when we test our patients, right? When we're not looking specifically for antigen specific activation, but we know that the nerves can activate mast cells to induce some types of hives. And I'm thinking, potentially cholinergic urticaria, although we don't know specifically, but it's a very similar to that.
So why don't we all develop allergy to venom, right? So that we all get stung, we all develop this itch, it's activating our sensory neurons. So what's kind of the key there?
So that is a great question. And that is something that's kind of led to some of the next things that we were looking at in the lab, which was, gosh, if we're all surrounded by allergens, and if we all have the ability to develop itch, right? We all have sensory nerves, we can all feel stuff. Why aren't we all allergic to everything, right? Why is it only 30% of people? So to get at that question, we kind of had to make some sort of hypothesis. We had to put our money down on something that might control it. And so as neuroimmunologists, we put our money down on immune cells and basically had the hypothesis that there was an innate immune cell, who knows what, that could be somehow setting that threshold for reactivity in the nerve. Now, this wasn't a crazy idea because Brian Kim had previously shown that activated Th2 cells or activated allergic T cells can pump out things like cytokines, like IL-4 and IL-13, which can change the threshold for reactivity for itch-sensing neurons. And that plays a really important role in atopic dermatitis. I mean, that's why dupilumab works so quickly, right? Because IL-4 and IL-13 really prime that itch response. If you take that away, you really take away a lot of that itch response quickly. So we kind of hypothesized that there was a similar pathway that might be working through the innate immune system. And actually, the most surprising thing for us was when we did a control experiment and took away the adaptive immune system and saw, oh, shoot, we've lost our allergic immune response. We've lost our response to our itch response to allergens, okay? And what we actually found was there was this funny cell that yeah, it's part of the adaptive immune system, but it's really an innate type of adaptive immune cell. It kind of like lives right on the edge, called a gamma delta T cell in the skin that seemed to be absolutely necessary for the itch response or neuronal response in general to all kinds of protease allergens. I mean, we were talking like, sure, like, yeah, dust mite, fungal allergens, but we're also talking things like fire ants, mosquito saliva, all this kind of stuff, all those itch responses depended on these cells. And so what we were able to do is we looked through, okay, what cells are these gamma delta T cells in the skin? And we found a really funny one that had been seen in the literature, but really poorly described. And we just named it GD3 for the third type of gamma delta T cell in the skin. We actually found that it was secreting at baseline IL-3, okay? And that IL-3 was necessary for this neuronal response to allergens, okay? So, okay, fine, we've just added another level, but how do we know whether or not this IL-3 pathway might be important in people, right? Because we did all this in model organisms. Well, to try and figure that out, first we looked at the gamma delta T cells in humans, and we saw similar transcriptional profiles. So it's not a smoking gun, but it tells you that these are similar cells to what we see in humans. And otherwise, we don't really have a clear analogous cell to the epidermal gamma delta T cells that we see in humans. So we think these might be it. But more importantly, what we saw is that the number of these cells and the activity of these cells is really dependent on certain environmental exposures, okay? So what am I talking about? Well, microbiota, okay? So whether or not you have a microbiota really depends on whether or not you have these cells, okay? So actually, we often think of germ-free mice as being all weird and being super allergic. We actually saw that germ-free mice didn't have these cells, and they weren't really susceptible to skin-induced allergy, okay? But what we found is that if we took these germ-free mice and we mixed them up with mice that had a normal microbiota or a normal lab microbiota, we found that these cells came back, okay? So there's something in that microbiota, whether or not it's the skin microbiota, whether or not it's the gut microbiota, that really seems to be controlling these cells. And that's kind of exciting because we know in humans that if you mess with somebody's microbiota, if you give kids antibiotics early, you really impact their risk of allergies in the long run, okay? And so I think this might be tying together this pathway. But the last reason I think that this cell is really important, this pathway is really important, is because if we think about how we treat itch and especially atopic dermatitis, okay, think about how important dupilumab has been, okay? Dupilumab has been such a wonder drug for atopic dermatitis, but it doesn't fix everybody, right? There are about 30 or 40% of patients, kind of depending on where you're looking, okay, that really have incomplete or fail completely in their response to dupilumab therapy. But a lot of these patients actually respond to JAK inhibition. And JAKs are these signaling molecules that are downstream of not only IL-4 and IL-13, from dupilumab, but are also downstream of a ton of other cytokines like IL-3, okay? And so we think that this IL-3 pathway might explain why some people that fail dupilumab still respond to JAK inhibition. And we're really interested in going into humans and figuring out, gosh, can this explain an endotype of atopic dermatitis that might help people and might help identify what drugs are the best for them?
So this seems like it explains a lot about the skin. Is this same process, do you think, going on in the lungs, going on in the gut, or are there different mechanisms there that are going on?
So we certainly know through our work and really the published work of people like Sebastian Talbot and Clifford Wolf, we know that a lot of the same neuronal control of allergic sensitization or developing allergies in the first place, we know that that is intact in the lung. Okay, so the lung seems like a similar picture. We don't know the specific neurons, and we don't know if these gamma delta T cells are playing a role there, or if another source of IL-3 or another cytokine in general is important. But we think that the same pathway is intact in the lung. The real question is the gut. Man, that the gut is a tough one, okay? Not only does it have a really fundamentally different nervous system, okay, because remember, it has everything that the skin has, but then it has its own nervous system, the enteric nervous system that innervates it. But it has all kinds of different immune cells and resident immune cells that are in the gut. And one interesting thing about the gut is, as we know from like the LEAP study, okay, if you give people antigens, if you give them food orally through their gut, it is really good at inducing tolerance if you give it early enough, okay? It's really not good at inducing allergy. And so I think a real fundamental question in the field, one that I'm really interested in, is, kind of that dual barrier hypothesis, which is really, okay, where does this sensitization happen? How much food allergen sensitization happens through the gut? How much happens through the skin? Where are the sites of exposure, or where are the sites of sensitization? And this is important for us because if we look for this pathway to be present in the wrong place, then we're kind of biasing ourselves against, what pathways really are controlling either tolerance mechanisms or allergic mechanisms.
Do you think there are additional ways we can use this as we think about patients and how we can prevent allergies? Is there a way to, stop this crosstalk between the neurons and the dendritic cells or these gamma delta cells? Do you see any way that this is going to be clinically important?
So one way in our work that we try to kind of play around with the skin to see, what sort of skin conditions would lead to changes in these gamma delta T cells. One way that we played around with it was to really dry it out. Those poor mice, they got itchy, they got dry skin, okay? And when we put them through a dry skin model, what we saw was that these gamma delta T cells really increased in number, okay? And so one thing that I'm taking away from that observation, and granted, this is in mice, this isn't in people, right? We're still trying to find out if this whole pathway is intact in people. But one takeaway for me is, gosh, good skin barrier function is like the best thing we can do. And what is barrier function in the skin? Like, sure, it is that keratinized layer, but it's hydration, right? So looking at solid skin hydration is, I think, incredibly important. Now, if we look at the clinical trials, to be completely honest, they're a little bit all over the place with this, okay? And people have a lot of reasons that they come up with one way or another. But based on what we see in the lab, I still am putting my money on skin barrier function, skin hydration to improve skin barrier function as some of the most important things. Now, the next question is, well, is the skin microbiota important? Well, it's hard because we're only starting to learn about what the normal skin microbiota is in the first place, okay? But I think that that is another potential area to really think about in the long run, okay? How we can kind of improve our skin microbiota and what that safe, non-allergic microbiota might be.
Yeah, we just don't know, right? There's so many different makeups of the microbiome in the gut, in the skin, and all these studies have been done with very different kind of balances of different microorganisms. And so I think that's going to take us a while to figure out.
Totally. I mean, even if we look at different areas on the skin, the microbiota on the face is totally different than the microbiota on the arm, And so I think it's way more complicated than we originally thought, which is fun for a scientist, but frustrating if you're trying to put this into clinical use now.
So I want to switch gears just a little bit. So in addition to your research and your clinical work, you lead the Stanbury Physician Scientist Pathway here at Massachusetts General Hospital. And this is the program that takes these internal medicine residents that are super excited about science and helps them to kind of along the physician sciences pathway. Tell me how you got involved in this program and what keeps you doing it in addition to all the other hats that you're wearing.
Wow. Yeah, no, I don't know. Sometimes I realize that there just aren't enough hours in the day to do everything that I really want to do. But somehow I keep on getting through it, mainly because I just ignore my email all day long. But yeah, so I have always been, as a physician scientist myself, I've always been really interested in that leaky pipeline, and actually what makes the leaky pipeline or what makes it leaky in the first place. And I remember going through, my own training. And I remember hearing people say, well, when you're as an MD PhD, when you go from your PhD back to medicine, that's going to be the hardest transition. And actually, I didn't find that it was that hard. I loved taking care of patients, and that was so exciting to be back involved in that. And I feel like the way that you learn at the lab really does help you as a physician. But the hardest transition for me, to be completely honest, was going from a clinical fellow who was at the top of my game clinically, helping people on a day-to-day basis, and then going back to lab. Okay. And it's funny because lab is what I love. I should have loved it. But you know what? It's hard in the beginning. You stepped away from it for a little bit, and you're also trying to get a project off the ground and up and running. And anybody who's spent time in lab knows that it is very easy to waste 6 months of your life banging your head against the wall or chasing a weird errant blot on a Western. And you walk away and you say, at a certain point, gosh, am I wasting my time? Am I just not good at this? I mean, the imposter syndrome comes in. And beyond the imposter syndrome, you want to be helpful. You want to do something for the world. And there's a point where you just don't feel like you're making any progress in the lab. And it starts to weigh on you. And there were moments where I thought to myself, gosh, should I even be doing this? And a friend said to me, when I was going through all of this, he said, Carrie, make them fire you, but you're not allowed to quit, and that advice kind of stuck with me. And what I would say is that after about 2 years of the lab, 2 years in the lab, it's like clockwork. I've seen it a million times. Things started going right. I fell in love again with the science because I was able to do hypothesis-driven research, and it became fun and exciting, and I felt like I was contributing to something greater. And all of that made me so happy that I hadn't quit. But one thing that I realized would have been really helpful along the way, because it wasn't just me that was feeling these things, it was so many of my peers. But we were all isolated and we were all in our silos, and we didn't have a community. And sometimes I think that lack of community leads or plays a really important role in that leaky pipeline, because when things get rough, you need that person to say, Carrie, you can complain all you want, but you can't quit. Make them fire you. Okay. And that I found was something that was so simple building that community. But it's something that had to happen early. People needed to know that they had a group with them that were going through the same things, that were going to be going through the same struggles. And so that made me really interested with how we were educating physician scientists, not in the MD PhD stage. We're doing a great job at developing there, but really how we were taking them through residency. Okay. Because residency could potentially be a place where you put everything on hold. But I wanted to keep a little bit of that side of their brain, of my brain, alive during residency. And so when I was thinking about this, Mass General had recently started a physician scientist program that actually didn't even exist when I came through. And they were looking for people to get involved. And I jumped at the chance to get involved and to kind of share my story with people, to share the imposter syndrome, to share how much you stink at certain points along your path, and that it actually can work out on the other side. Because I feel like that community, that near peer, that that near peer and more official mentorship, that is so important in making you feel like you're not alone and that this is worthwhile and that you just got to stick with it. And so it was that drive to build a community that got me involved in the first place. And then I think it's been my passion for, building that community and building really a diverse group of scientists that think about different scientific questions so they can excite each other and excite new questions and new potential opportunities for collaboration. And, just building that group of people that can become those touchstones as we move forward, that really has been something that has been such an exciting thing to see develop and to mature here at Mass General.
I think community is just so important in so many different things, but you're right that I think as a physician scientist, it's easy to put your head down, get excited about the experiments, but not build the community around you that can help you when nothing is working, or even
Exactly.
help you celebrate when everything is working.
Yeah, and for the things are not working more often than you're celebrating. So you've got to find a way to actually enjoy those incremental steps and to enjoy a little, or at least find humor when things don't work.
So, speaking of community, I wanted to talk a little bit about the Discovery Program that's a part of the Quad AI World Allergy Organization Joint Congress. The last year was the first year of it, and this is going to be the second. Tell us about the development of the Discovery Program and why it's so important.
Yeah. So my first time attending the Quad AI was as a PhD student when my mentor actually wasn't able to come and give a talk, and so gave me the opportunity to give a talk at the Quad AI. And I just remember being floored by the quality of scientists and the fact that there were so many scientists who were interested in type 2 immunity. There was absolutely no meeting that attracted the same breadth and depth of researchers interested in allergy, immunology, etc. And that made me fall in love with the Quad AI right off the bat, and has made me, continue to come to those Quad AI meetings. It's something that I love. But I do think the size of the Quad AI is overwhelming, okay? And I've been going to these Quad AI meetings for over a decade, and I still get overwhelmed by the size of it, and I can still get lost. And if that happens to me after building a kind of a network of scientists here, how do other folks feel? And is this a good opportunity to get trainees involved if they just feel like they're so small in the sea of researchers? And so what we really wanted to do is we wanted to build, again, it's all about community, build community amongst the scientists at the Quad AI by making something a little bit smaller, by taking a bite out of that gigantic, beautiful meeting and focusing on basic science, where we could get everybody together in talks that were not overlapping so we could all sit through and see each other's fantastic work, and to make it a little bit smaller so people felt like they could present really brand new, hot off the press, or actually before it has even hit the press, research. Okay. We wanted to take advantage of the fact that type 2 immunity has no better home than the Quad AI, and really bring all those researchers together here and make this the premier basic science meeting for type 2 immunity, as it already is for clinical and translational type 2. So that's really was the excitement and the genesis of this. So I was one of the people that got really excited about it and pushed it forward. But the people who really did all of the work, I mean, we're talking Nora Barrett, who really got the first meeting up off the ground and running. And it was such a fantastic success that I'm hoping we can repeat it this year and keep on moving forward with it.
Absolutely. And actually, as we air this, the registration is actually quite full. So we may actually be capped. But hopefully the people that are really excited about being there can be there and we can continue to expand this program. Do you have any highlights from last year that you feel like really times you're like, oh, this is great, seeing what's being done, building this community?
Well, I mean, that there are so many highlights. I mean, I think honestly, my the best highlight is actually the poster session. Okay. We had, because we were a smaller meeting, we had the ability to have a poster session in a room where we could all be together and you could walk through, and all the trainees were at the posters, and you had all of the PIs kind of walking through and learning their science and giving feedback. And honestly, it was electric. It was such a fun atmosphere. We got to meet so many people. I got to meet people at all levels of training, okay, as well as other folks in type 2 immunity that I'd never met before. And really, it was just a great way to learn science and to meet the people who really are changing the field, okay? So that was honestly my favorite part. But I would have to say that the question and answer sessions for all of these talks, like, they were also so much fun. I mean, the give and take, the conversations that came out of it, pointing out the flaws and pointing out next steps. I mean, that's what makes science better, and that's what makes all of us, want to be engaged. So that was such a joy.
I just want to thank you again for coming on and talking to us about neuroimmunology, and for providing the advice that, when it gets really hard, go to your community, don't quit, make them fire you. I love it. That's a great advice for scientists that are really struggling at times to kind of build that. Uh, is there anything else that you'd like to add before we sign off?
I what I would say, the only thing that I would add is that if you're listening to this and you are involved, or you're thinking about a great way to apply yourself in immunology, or clinically, whether or not it's at the bench or the bedside, I would urge everybody to think about allergy immunology. And I would urge everybody to think about specialties that maybe you don't think about every day. Okay. Every day when I talk to people, to trainees and to applicants, they often say, gosh, why did you get involved in allergy immunology in the end? And I talked about it a little bit before, but really fundamentally, it comes down to, do you want to be the first person to figure this out and be 3 months ahead of somebody else, or 30 years ahead of somebody else? Do you really want to actually play a role that nobody else would be stepping into? And I hope that honestly, in 15 years, we'll just all be like maybe 1 or 2 years ahead of other people. Okay. I hope there'll be so many investigators that it'll change in allergy immunology. But I do think that this is a field where you can make such an impact on the science, on your patients, on your fellow physicians, in terms of education. And we just need more people. So if you have the passion, we've got the space for you.
Absolutely. And I hope we'll see lots of people at the AAAAI World Allergy Organization Joint Congress this year, and that they'll all come with their questions and then find the scientists that are giving the talks and ask them, so we can make the field even better.
Thank you so much, Rebecca.
We hope you enjoyed listening to today's episode. Please visit quadai.org for show notes and any pertinent links from today's conversation. If you like the show, please take a moment to subscribe to our podcast through the Apple Podcasts, Google Podcasts, or Spotify, so you can receive new episodes in the future. Thank you again for listening.